So today we're going to talk about random projections in the context of dimension reduction. And so we'll talk about how to do dimension reduction in random projections, and in particular the celebrated Johnson-Linde-Strauss lemma. So we saw already before that if we have data sets in high dimensions, there's oftentimes a hope to project this data set to a lower dimensional subspace, or just project it to lower dimensions in a way to keep many of the properties of the data set, right? This was the idea of dimension reduction. Right, so dimension reduction. Right, the idea was if we had some data set, say S, for example, the set of points x1, xn, right? Endpoints, say, for example, right? Endpoints in d dimensions. Right, then we would like to take a map that takes these points, right? Takes points from d dimensions and puts points in a much smaller dimensional space, let's say Rk. We should think of K as much smaller than D, such that somehow the geometry is kept, right? Like it preserves the geometry, or sort of informal way, geometry is kept. Right, so we did this to some extent with principal component analysis and the diffusion maps. Right, examples could be, say, PCA, right, diffusion maps for sort of the linear and nonlinear version of this. Here, what we're going to see is we're going to see one of the examples of the so-called blessings of high dimensions, or concentration of measure, in which you're going to be able to do this with random maps. So you're going to take F, this is going to be built via sort of random linear maps. It's going to be a random linear map. And what we're going to see is because of concentration of measure, if I take a random linear map into dimension K, as long as K is sort of big enough, then we're going to be able to understand exactly how the geometry of this, how exactly the geometry of the set is going to be transformed. Because of concentration of measure, we're going to be able to predict this very well, and in particular, we're going to be able to understand when is it that it doesn't get perturbed, right? So for which value of K we can do this. So let's first make a few observations, right? So if K, if K is, right, okay, let me put it this way. If N, right, so just start with an observation. Maybe I'll make this observation here. Right, so if D is much bigger than N, then it's easy to take, right, easy to do with just K being N. Right, because all the n-points will lie in some n-dimensional subspace, so I can just take the projection on that n-dimensional subspace, right? N-points in d dimensions, if D happens to be bigger, then, they really only belong in n dimensions, right? Whatever dimensions they span, and so, of course, this is sort of completely trivial, right? Not even easy, it's like completely trivial and not interesting, right? We want to ask when D is bigger than n. Right, and in particular, that is easy to do, and being as an isometry, right? Like the map F would satisfy, F would be an isometry, right? Is an isometry. Right? In particular, F would satisfy that for all pairs of points I and J, right? We'll just project them, everything stays the same. F of xi minus f of xj, right? So the projections minus f of xj, right? Norm will just be equal to the norm, right? It preserves all the distances, right? And if it preserves all the distances, basically preserves all the geometry of the points, right? Because if you preserve all the distance of every pair of points, then your points really didn't change at all, right? So now, and F is a linear map, right? So now we can ask, what if, right? What if we allow, right? What if we allow some kind of error, like 1 plus or minus epsilon error? Right, so what I mean by this, what if we allow our map F that goes from Rd to Rk to preserve in the following sense, that we want that every point, it's an almost isometry. In the sense that if I take this square, this is smaller or equal than 1 plus epsilon, right, times the norm, the distance, the original distance between the points, and 1 minus epsilon times the original distance between the points. Okay, sorry. room. Right. So what if I allow for this? Can one get smaller? Can we get a smaller k? Can k be smaller? Okay. Right. So this is the type of questions we're interested in, and in particular, the answer to this is given by the famous, celebrated Johnson-Lindstrauss lemma from the mid-80s. But before I talk about this, let me just give you sort of a bit of a vision of where we're going with this. Not only are we going to be able to, what's the advantage of being able to do dimension reduction this way? Well, one advantage is if we're going to do random linear maps, then we can potentially do it without seeing the data set, right? We're going to potentially be able to just take a random linear map, and we will work for the data set in question, and we can pick the projection without even seeing the data set. And so that will have, right, many, many advantages. One, we can do it online or streaming. If we're getting one data point at a time, we can project the first data points without having to see the last data points in the set, right? This will be very, very useful. But it goes further, right? Another big advantage is that, let's see if I can give a good description of where I'm going with this, and we will get there. We'll do enough, we'll do the math to support what I'm saying. But if you have a good understanding of how many dimensions you need to project do a random linear projection in order to keep the geometry of a set F, then as we go further, then in the next lecture, we're going to be able to do this not just for any set of n points, but actually exploiting structure of S. And then I can start asking S to be sort of non-explicit data sets, right, or abstract data sets. Like I can ask S to be all possible MRI scans of a brain, say, or MRI scans of something. Okay. Now if I ask for that, what I'm saying is I want a random projection, right, maybe, or pictures or natural images. Right? S can be the set of all natural images as they live in R to the D, where D would be the number of pixels of the images, right? So D would be huge, but the size of the possible natural images is not every point on R to the number of pixels, right? If I just put real numbers at random in the pixels, then you're just going to see gibberish. It's not going to look like a natural image. And so if I take S to be the set of natural images, the set of all possible MRI scans for the brain, or things like this, if I have a good understanding of what dimension do I need to take a random projection to, then basically, this random projection amounts to taking only k linear measurements, rather than taking a measurement for each pixel. And so this means potentially that if we understand which k works for sets like that, we can actually avoid taking the full picture or taking the full MRI scan, and we can just take k, say, random linear measurements of this. And so potentially you can reconstruct a picture not just by taking the value of each pixel, but by right away having the camera take a random projection of the image it sees. And if it preserves the geometry of the images, then maybe, just maybe, you're actually able to, from this projection, reconstruct the image back, right? Because, it will be that all the images, if two images have a big distance, then after I project, they still have a big distance. So there's some kind of stability in this process, so maybe we're going to be able to reconstruct, right? And for images, it means that maybe you need less pixels, right? This is at the heart of a technology known as compressed sensing, which we'll talk about for a few next lectures. And sort of the beginning of it, in a way, comes a bit from here. And in fact, there's a camera called the 1-pixel camera, which uses exactly this type of approach. And there is an approach to speed up MRI scans that's basically exactly on the idea that if you take measurements that correspond to some kind of random linear measurement of some type, they should be somewhat structured because the MRI machine has sort of physical limitations, then potentially you can actually do, say, MRI scans with a lot less measurements, which means the patient needs to be a lot less time in the machine. And so this is could be very beneficial, especially if the patient really can't move, and there's cases on which you actually don't even want the patient to breathe and things like this. So there's some cases where it's really critical. But my point is that as we're going to be able to understand bigger, like more complex sets S, we're actually going to be able to use sort of this technology, as we'll see. We'll have to develop it quite a bit to explain this phenomenon that when you want to measure like an MRI scan, natural image, and as we'll see, actually even recommendation systems like matrices of when you go online and to some shop and they sort of suggest you a product, and they have a good belief that you're going to like this product or at least want to buy it. Right? This is done by thinking of a big matrix of sort of users and products and thinking what would be the ratings if they were to buy it. Right? And they have some ratings from the people who bought it and rated it. And now this matrix is also has some special structure. So I can also think of the matrices that form natural sort of user product rating system. Right? These matrices are believed to be low rank, and so we can study S to be the low rank matrices, for example. So we'll see a bit all of this. I just want to sort of give you a bit of vision to what's about to happen in the next few lectures, that once you understand random linear projections very well, this phenomenon of this splicing of high dimensions of sort of the concentration of measure that's behind the reason why this works, then you're actually going to be able to see what's at the heart of things like compressed sensors and low-rank matrix completion, recommendation systems, and so on. Right? So the fact that the map is random means that you don't even need to see the whole data set. So you can do it streaming, but even more means you can think of data sets that are sort of abstract, right? I mean, they're just things like all natural images, all brain scans, all telescope images of the night sky, things of this style. Okay. So now let's go back to our example and let me describe the Johnson-Lindstrauss lemma. Right. So Johnson-Lindstrauss basically answered this question. How small can K be? And they answer that K needs only to be of size log n, not n, right? So these are huge savings, right? And then we'll prove Johnson-Lindstrauss lemma. Okay, so let me I'll erase everything. Okay. This is from 1984. Okay. And they say that if K, if K is bigger than, I believe it's log n, okay, let me make sure I get this right. Yes. Then for all sets of points, and for all sets of n points, right, there exists F, a linear map from R D, right? There are points in R D. There exists a linear map for RD to RK, linear, such that F is an epsilon isometry. It's an epsilon almost isometry. So what I mean by this, such that for all 2 points xi xj, we have the following, that F of xi minus F of xj in L2 norm is smaller or equal than 1 plus epsilon xi minus xj squared then 1 minus epsilon xi minus xj squared. Okay, so you don't have maybe necessarily really an isometry. Maybe I should move log n over here just so that it's more clear. This is log n times some cost. If you this is a beautiful result. all you need is the k to be bigger than log n times some constant that depends on epsilon. Then, for any set of endpoints, there is a random linear projection, not yet random, that preserves the distances between every point up to epsilon, right, in this form. Moreover, f can be found, like f can be found in randomized polynomials. Be found in randomized. So this is not yet a statement about what happens when I take f random. In particular, here we will have to find f. We'll see from the proof where this happens. But it's already saying that, you know, regardless, if I have any points, even if they're in very, very high dimensions, then projecting to logarithmically to log n dimensions, where n is the number of points, is enough to sort of preserve the structure of 2 epsilon. Moreover, this is actually known to be optimal. So you cannot improve, maybe you can improve the constants, but you cannot improve the behavior of 1 over epsilon squared times log n. Right? This statement is not true with better dependency on epsilon and log n. This was actually proved rather recently. Now we're going to prove this. The idea is that we're going to take f to be a random projection, and given, you know, we're going to prove that the random projection has a reasonable probability of succeeding. So all we have to do in order to make this theorem work is we have to try, you know, if you get a data set, you have a reasonably good probability of succeeding. So you just try many times until you see one. And you know, because you have a reasonably good probability of succeeding and all the trials are independent, that eventually you will find something, and you'll find something in randomized polynomial time. It should take you only around actually n times. But then we'll see also that adapting the proof is not even hard to see that if k is a bit bigger than this in a multiplicative sense, then actually you just have to pick up one map and the random map will work. Okay? So that's what we'll see now, but we'll first prove this statement put this way with you know, just a specific map that you may have to find, because this is the classical Johnson-Strauss lemma. So in order to understand what happens to random projection, we're going to need consideration of measure result about projections, right? It's very similar to things like opting and Princeton type inequalities. It doesn't quite follow from those because the random variables are not, you know, they're not naturally bounded, but it's exactly the same type of proof that gives this simple argument. Okay, so we do the following. Okay, so lemma of concentration. Let U be uniform as C minus 1, uniform, right? Uniform randomly in the sphere of dimension D. Right, so I take a random point, unit norm point, right? Is in the sphere, which means U as 1 and it's uniform there. Then what I want to understand is if I take a projection on a k-dimensional subspace of this, what is the norm that I get, right? Because the vector U is random, right? It's the same thing, and this will be key in the proof, making the vector random and the projection fixed, or the projection fixed and the vector random, right? So I'm just going to take a map G. Is going to be the projection, G, is going to be the RD to RK, right? It's going to be the projection on the first k coordinates. K coordinates. Right, by the way, it's good maybe to make a point that one way you could take U, for example, is you could take a Gaussian, say, Y over the norm of Y. Right, where Y is a Gaussian vector, for example, right? Because Gaussians are rotation invariant. It doesn't matter. They don't have any preferred direction. So if you take them over their norm, they're just uniform in the sphere. So that could be a possibility of how to draw such a point. Right? Okay, but that's not really important. So now it's the projection on the first three coordinates. So what we want to understand is what happens to the norm of of this projection. So we want to know the distribution of the random variable L, which is the norm of projecting this random vector on the first k coordinate. So I take a vector with norm 1. I look at what happens with. I take a vector of norm 1. I project it on the first k random. I project it on the first k coordinates, and now I ask, what is the norm squared of what's left? Right. So we expect that the mass L should be very concentrated around roughly k over d. Right. The square of each entry should be roughly 1 over d. So we expect that this random variable should concentrate very well around k over d. And this concentration measure inequality just tells you how much it concentrates around. Right, so I'll write it here. If b is smaller than 1, then for this we have, this is what we'll use, the probability of if this random variable L is smaller than k over d by a multiplicative factor smaller than 1, smaller equal than exponential of, you get k over 2, and then you get this expression. You get more room, 1 minus beta plus log beta, right? And we have the same thing for beta positive. So if beta is bigger than 1, right, you get the probability that L is bigger or equal than beta k over d. Right, and the proof of this is very simple. You can think of it, if you think of this as just Gaussian vectors, it's just comparing the norm of the, right? If you think of it this way, it's just comparing the norm of the first k Gaussian squared compared with the norm of all the other Gaussian squared. And so then you get this, essentially right away. 2, 1 minus beta plus log beta. Right. And it's not so hard to see that basically, this, as we'll see from a Taylor expansion type thing, essentially, this inequalities look the same because basically this looks a bit like, 1 minus beta squared over 2 minus that, right? So it's like epsilon minus epsilon squared over 2, where if epsilon is, if beta is, we think of it as 1 plus minus epsilon, right? Minus epsilon here plus epsilon here, we here get some kind of minus epsilon squared over 2. Okay, so this is the inequality we're going to use. Right, so now essentially this is all we need, because now with this inequality, then it's actually quite easy to prove the theorem. Because now let's say that I have my points, right, x1, xn, right, in Rd. Right, and now I'm going to take f. I'm going to take f to be a random projection on a subspace of dimension k. Right. Or let me actually make G, right? Because G is the projection. G will be a random projection on, right? A random projection on a subspace. Projection. Okay, I should say projection on a random subspace. Okay, I should do G prime just because this one is fixed, sure. But now I know that, the typical norm, I want that when I do the projection of something with a certain norm, say I'm going to do the projection of xi minus xj, who has some norm, I want the norm to be kept, right? But the norm here goes from 1 to k over d, so I should take f to be, right, square root of d over k times g, right? This is really what makes sense, and so this is the distribution I'm going to take. I take G prime, a projection on a random subspace, and I take my linear map to be just a scaling of that G, because if I have something norm 1, if the difference xi minus xj is norm 1, I want it to still have norm 1 after the projection. So I need to scale by square root of d over k so that I get the square and cancels this out. So now let's look at a pair. Let's fix xi minus xj. Right? Let's look at a pair xi and xj. Right, and let's take u to be xi minus xj. Right, and what we're going to try and do is we're going to try to compare, right, the norm of u squared versus the norm of fu squared. Right, because u is xi minus xj, f of xi minus xj, because it's linear, is the same thing as f of xi minus f of xj. So this is really the comparison I want to make. But now u is fixed and f is random, but it's exactly the same. You know, if I have a vector u fixed and I take a random projection, right, completely uniform, this is the same thing as fixing the projection and considering u at random. Right, it's exactly the same thing. Right, so thinking of u fixed and f random is exactly the same thing as thinking of u random and f fixed. So the distribution, so without loss of generality, of course, I can take the norm of u to be 1, right? Because I can just rescale if I want. And then the norm of fu, right? What is the distribution of the norm of fu squared? Right? I take my vector u as norm 1, and I'll take a random projection on the K subspace, I take the norm squared. It's exactly the same thing as considering u random and fixing the projection, right? I'm just randomly rotate my space to make the projection be a fixed one. So this is exactly the same distribution as L scaled by the factor here, right? So exactly the same distribution as D over K times L. Right? And so the distribution of this quantity is exactly D over K times L. I mean, in particular, if the norm of u is not 1, then basically what I'm saying is that, you know, I can rescale. And so this quantity for fixed u, for fixed xi, has distribution exactly D over K L. Right? And of course, I can take this a step further, and I can take fu to be xi minus xj. Because of linearity, this is the same thing as saying f of xi minus f of xj. Right? And so this is equal to, right, the distribution of this is exactly the same as the distribution of this, is just distributed like D over K times L. Right? So now I can use those concentration inequalities. Right? Because now this means that, you know, the probability, if I set, okay, let's start by setting beta to be 1 minus epsilon. Let's look, right? So if I set beta to be equal to 1 minus epsilon, right, what do I have? Right, I have that, you know, the probability that that quantity for a fixed xij, of course, is smaller or equal, right? Because now this is L times D over K, so it can take out this one, right? And now the smaller, and probability this is smaller than 1 minus 1 epsilon. Is, right, the probability that this happens is smaller or equal than this quantity. Right? What is this quantity? Okay, I'm going to erase everything and keep going there. Right? What is this? This is smaller or equal than exponential of k over 2. Right? And now I get what? I get that, right, 1 minus epsilon. So I get epsilon, right, 1 minus 1 minus epsilon plus log of 1 minus epsilon. Right? Did I close all the parentheses? No. Okay, so I have this. Now, by, you know, you can just do Taylor expansion, and this is bigger or equal than or smaller or equal, sorry, is smaller or equal than minus epsilon squared over 2, right? So then what do we get? I'll try not to erase that. We get that this is smaller or equal than exponential of k over 2, and then, right, the minus epsilon cancels with that one. I get minus epsilon squared, so the minus can go over there, it'll be a bit better. K over 2, epsilon squared over 2. Right. Now remember the condition, right? K needs to be bigger or equal than 4 times 1 over epsilon squared over 2 minus epsilon cubed over 3 times log n. Right? So if k is bigger than this, it's also bigger than this without this number. Right? And so I can now replace, because there's a minus, right? I can just replace, right? I can just replace k by this quantity without this number. Right? The epsilon squared over 2 cancels with this epsilon squared over 2. Right? Then 2 shoves off a factor of 2 of the 4, and so I get 2 log n. Oh, sorry, an exponential of 2 log n. Right? So this is equal to n to the minus 2. Right? So the probability that the norm undershoots by more than a factor of 1 minus epsilon is bounded above by 1 over square root n. 1 over n squared. Now we can do the exact same thing for the upper probability. And basically, the exact same thing happens, it's just that here you have 1 plus epsilon. So when you bound it above, you need actually the cubic term. This is exactly, the cubic term shows up in exactly this way. And so basically, this is exactly why this condition here, but the same thing is true, right? You should check it. But this follows, it's exactly the same argument, it's just there's a cube, you need to go up to the cubic term, right? Because now the cubic term is a different sign, but it exactly shows up exactly this way. So we get the exact same thing, that the probability that, you know, this overshoots by more than a factor plus epsilon is also smaller or equal than, well, it's also smaller or equal than the same thing. I could just put, okay, maybe I want to write it a bit lower. Or a bit smaller actually, so probability of this fraction overshooting by more than 1 plus epsilon will be smaller or equal also than n to the minus half. Right? It's exactly the same argument. So in particular, it means that the probability that, you know, this fraction is not in the interval, right? Not, the probability that it either overshoots or undershoots, so the probability that this is not in the interval of 1 minus epsilon, 1 plus epsilon, right, is smaller or equal, then we can just union bound, right? So it's smaller or equal than 2, n to the minus 2. Right? So this means that, you know, with probability 1 minus 2 to the n minus 2 for these pairs of nodes, for these pairs of points, this ratio is actually between 1 minus epsilon and 1 plus epsilon. But really what we care about is what's the probability, right, that, you know, what's the probability that, what is failure, what is success here? Is if you're inside the interval for every pair of points I and j. So the question is, what's the probability of there existing a pair I and j such that this is, right, such that this, let me write it, I'll write it the first time, the last time. Is not right? This is what failure is, right? This is really the event of failing to be an epsilon isometry, right? This is failure. And now what's the probability of failing? Well, it's the probability of existing, it's the union of this, of failing for each pair of I and j. So by union bound, this is smaller or equal than the number of such pairs, n choose 2, and times 2 n to the minus 1. Right? But now we can just work this out. Right? What do we get? We get n minus 1 n over 2. And then we get 2, 1 over n squared. Right? One of these n's cancels with that one, the 2 cancels with that, and we get n minus 1 over n. So this is equal to 1 minus 1 over n. So the probability of failure is smaller or equal than 1 minus 1 over n. So the probability of success, right? So let me write here, the probability of success is bigger or equal than 1 over n. Right? So it means in particular that if we try it n times, or 2n times, or 3n times, but a multiple of n times, then we will find something that works. Right? And we can check it. Right? In polynomial time, we can check it. So we just need to try, order n maps, and one of them will work. And this is how you prove Johnson-Linus-Strauss lemma. Right? This is the end of the proof. Now, of course, from the application viewpoint, this is not right. This is not great because you have to try a bunch of maps. You have to go check them. In particular, I sort of promised that we're going to do this for either abstract sets or streaming online sets, and this doesn't work for that, right? Because if you have a set that's coming one at a time, and right, and you want to be able to compute the projection before you see the last of the set, you get like 5 points. You want to compute the projection of those 5 points before you get the next 5. Right? You cannot go and try a bunch of them, and then because to check if it succeeds or not, you would have to try it in all of the data sets. But now the point is that this is actually easily improvable, by just asking a little bit more. Right? All we need is to get here a bit of better probability, and then we're done. Right? So if we ask, so now I'm going to just change the proof just slightly. If instead of 4, we ask that this is bigger than 2 times 2 plus some tau, right? So just a little bit more. Then when I run this argument, I get that this is the probability of failing is smaller or equal than n to the minus 2 plus tau, right? Because the 2 came over exactly from over there, right? Because it was, when I, right, from here, it was going here, this 2 was exactly that 2. Okay, so right, same thing here. We would get here, we would get here 2 plus tau, right? But now here we'd get 2 plus tau. But now when we look at this proof, we have 2 plus tau. Right? But now if we think about what happens here, right, plus tau again, right, this is smaller or equal than, 2 constants, I won't care what the constant is, 1 over n to the tau. Right? And in fact, even exactly. Right? Because, we would get n minus 1 over n of 1 plus tau, which is smaller or equal than n minus 1 over n times n, right? So this is equal to just n minus 1 over n times 1 over n to the tau, right? So it's smaller or equal than 1 over n to the tau. So if tau is a positive constant, then the probability of failure is going to 0 with as n goes to infinity, right? So it means in particular that if this is satisfied, then a random linear map, right, a random linear projection, right, a random linear map, defined in the way that we defined it, works with probability. Right, is an epsilon isometry on the points, right, on S or on x1, xn, with probability bigger than 1 minus 1 over n to the tau. Right? And so if say we take tau to be 1, right? So we're just getting a little bit more, or say 2, we're just needing double the dimensions. And then the probability of being an actual isometry, when we just pick 1, is already 1 minus 1 over n squared. Right? So then it's sort of, it's weaker in the sense that we need now a bigger constant, but it's stronger in the sense that now we don't actually even need to look for the map. It's just a random map. And now if we do that, it allows us to do this for streaming data sets. Right? Now this can be an online algorithm. You can think of, you're studying something, you have a website people are visiting, visitors are coming on the website and want to study something about this data set, you can grab, if each visitor, their information is maybe a vector or something, you can just take projections of these vectors to a dimension like this, and you know that the geometry of these will be kept. Right? Or at least that, no two different vectors will be projected to the same thing. Right? So it gives you a hope of being able to invert if you know something about the set S and so on. Right? So let's keep thinking about this stringy example. Right? We have data points that are coming in. We drew a random linear projection, and now we have points that keep coming in. Okay, maybe I'll keep this on board. Okay, so we drew a random projection F. Let's represent it with the matrix M, right? Our random projection. Right? So this matrix M is equal to, right? It's a matrix. Okay, let me write it as a matrix. Let me draw the matrix. Right? And as dimension D on one side, and dimension, right, here will be something like roughly 1 over epsilon squared times log n. Right? Up to constants, right? This is what I mean by up to constants, right? So this is the matrix M. So now as points come, right? So when a point X comes, we project it, we compute M of X. Right? This is how we would, as we get data points, we would project them this way. But how much computation does this cost? Right? In general, if you want to do a matrix vector product, right, the computational cost of this, of projecting one point, right, is roughly the number of entries in the matrix. So we'll have a computational cost of roughly, 1 over epsilon squared log n times d. Right? D not in the log, of course. I'll put it a bit more separate. So if we're in cases where we really want to be efficient, right, this might be too much. And in particular, there's no reason why, there's no reason why for every point we should have to take time that scales like for every entry. It takes, for every entry of this vector, the cost we take is the cost of the entire size of the dimension where it's going to. Right? There's matrices where we can do matrix vector products much. Right, so can this be improved? Right, that's the question that I now want to address very briefly. Right, can this be improved? So the number of rows is essentially optimal. Right, this is known. So number of rows. Right, so number of rows, or K, is essentially optimal. So there's not much room for improvement there. But maybe we can get matrices M where the computational cost of matrix vector product is better. Right? So I'm saying now, instead of taking a random projection just completely uniform, maybe we can come up with distributions over matrices M that are sort of smarter from the viewpoint of computation, such that we can make matrix vector products much faster. And then we'll try to prove that it still satisfies the max properties of Chance-Lindestraat. That, I take M from some other distribution of random projections where their fast multiplication is available, and I still have that this still, with high probability, keeps the geometry of my data set and so on. So what are possible attempts, right? So let's think about attempts. So what could be, I take M to be a sparse matrix. Right? I don't mean M a fixed sparse matrix, right? I mean take M a random projection of matrices whose entries are sparse, right? So you're not taking all possible projections, you're just taking some. Right? So of course, even if this works, the proof will be a lot more complicated. You no longer have this rotation invariance and so on. But let me put the proof part under the rug. Let me not talk about this. So what's the issue of this? The issue is that, indeed, matrix vector product is much faster, right? If the matrix M is sparse, there's a lot of zeros. You can multiply matrix vector much, much faster. In particular, you don't need to multiply entries of the vector by element 0 in the matrix, right? So it's faster. What is the issue? Is that in general, you will tend to distort, right? To give distortion of sparse vectors, right? So you will have a tendency to distort sparse vectors. Why? Because if matrix M is sparse, the matrix M is sparse. Let's say it only has a few non-zero entries, right, in each row. Then if X is also sparse, then, you know, when you take the inner product, right, when you take the matrix vector product, which is the inner product of rows here with these columns, you will see a bunch of zeros, because most things will be zero unless the non-zero entries happen to coincide, or at least have a collision. So in general, sparse matrices, you know, sparse short-fat matrices, our projections, will be quite bad at projecting sparse vectors. And since you don't know if the vector is sparse or not, this fails because of this. Right? I mean, at least intuitively. One, you know, I would have to try and it would have to explain why, you know, what distribution of sparse matrices and so on, but in general, this is the issue. So another attempt is to use the fast Fourier transform. Right? There's non-sparse matrices that we know how to multiply very quickly. One of which is the fast Fourier transform. So we could grab X, right? Take a fast Fourier transform. Right? This takes time roughly d log d, right? Even though it's a d by d matrix, this takes time only d log d. Right? This is a beautiful algorithm. And it's very, very important is that you can take the Fourier transform of a vector in time d log d. You don't need time d squared. Right? And then right, you get like the Fourier transform of X. And then maybe you take a projection by a sparse projection. Or something like this, right? This could be a possibility. Right? Or another way of thinking about this is you're somehow just taking a few of the rows, maybe, of the Fourier transform or something like that. Right, so this is attempt 2. Right, it's the natural attempt 1, attempt 2. What is the issue? Right, the issue is that it will distort vectors whose Fourier transform is sparse. Right, if X could have sparse Fourier transform. Right, so the issue will be vectors whose Fourier transform is sparse. Right? This is the issue. I mean, it's just exactly the same issue. So how do you reconcile this? How do you fix this? Right? One, there's this really nice idea, right, which is that we exploit the uncertainty principle. So essentially, I mean, I'm being extremely vague, but I just want to give the very hand-wavy, but I just want to give the idea. Right? One form of the uncertainty principle says that in general, I mean, X cannot be sparse, cannot be both sparse and have sparse Fourier transform. And so somehow X cannot have this issue, for a vector X, they cannot have this issue at the same time. Right? And of course, you should think of the vector X as like xi minus xj, right? Because that's the vector you want to keep the normal, and we can not distort very much. Right? So because of this can actually be exploited in a really clever way. And the idea is the following. So let me see if I can give very, very hand-wavy, very superficially what the idea is. And the idea is to try to break these issues, still have a fast transform, and exploit the fact that nothing can be both sparse in the Fourier transform and the sparse matrix. I mean, you could try to do both projections at the same time, something like this. But there's something even much nicer, which is you take a vector X and you randomly flip. So you randomly flip the sign of entries. Right? So you take dx, where D is a diagonal matrix with random plus or minus ones in the diagonal. Okay, so this step takes time D, right? X is the vector in Rd. You're just randomly flipping each coordinate. This takes time just D. Now the point is, okay, if X is sparse, then, right, this change didn't do very much. But if X is not sparse, then this changed it a lot, right? Because if X is not sparse, then you basically completely randomize the signal. And so now the point is, because of that, this is also, in a way, a consequence of the uncertainty principle, it will, with high probability, will not have sparse Fourier transform. Right? Then, I mean, they use the NMR transform, but it's the same idea, right? The idea being that if I take a vector, if, if X was sparse, then it didn't get very randomized, and so maybe it could be very structured, but then dx would be sparse, therefore its Fourier transform wouldn't be sparse. If dx is not sparse, then potentially its Fourier transform could be sparse, but it was super randomized, right? Because X has almost no zero entry. So every entry got flipped, it got completely randomized, completely shuffled around. And so one can show that with high probability the Fourier transform of this won't be sparse, or some kind of NMR transform. And so you hit it with another matrix H, right? You take an FFT or a NMR transform. Right? Doesn't really matter. So we take it of a matrix H. Right, think of it as a Fourier transform matrix or some kind of fast transform. And now we get a vector which is X, which is H dx. And now, because we know that for sure this is not sparse, at least with high probability, and you can control these things, then we take a sparse projection. And this is what the authors of this paper call P matrix P, and so they get to something they call PhD X. So you do this step where you hit it with the matrix D, diagonal plus or minus ones at random. Then you hit it with some kind of transform like an FFT, and then you do a sparse projection. And the computational cost of this, right, computational cost, is actually around D log D. Right, instead versus the trivial, D 1 over epsilon squared log n D. Right, in general, we expect n to be much bigger than D, right? Generally, you have more points than dimensions they're in, and so this could be substantial savings. Right, in particular, just reading each data point takes time D, so D log D is not, is not much bigger than D. Right, and so this is the idea behind fast Johnson-Lindströms. What's called fast JL. Right, and there's many different ways of doing fast JL. This is one particularly elegant way. I mean, there's still a lot that goes into proving that, right? It's clear that this is fast to compute because it's fast to compute B, it's fast to compute H, it's fast to compute P. But I would still need to prove, of course, that this, the randomness in this is enough to still be able to carry out the proof, right? The proof is more sophisticated for sure, but can be done, and this is the idea of the fast Johnson-Lindströms. If you look in the notes, there's references for the paper that proposes this. And so what we're going to do next is we're going to address more general sets S. So sets S in RD with extra structure. And we're going to try to understand how many dimensions we need to project them to in order to keep their geometry. And in particular, thinking about sets S like the set of all natural images, or the set of all possible brain scans, or the set of all possible reasonable user product ratings, and so on and so forth. And we're going to derive a lot of the scalings and predict a lot of the scalings that will hold in things like compressed sensing, sparse signal recovery, and matrix completion, and so on. Okay, thank you.